In this episode, we take the same practical, pattern-based mindset that security teams use for apps and apply it to machine learning, ML, systems, using guidance associated with the Open Worldwide Application Security Project, OWASP, as a way to organize our thinking. The goal is not to turn you into a data scientist, and it is not to bury you in math, because you can understand the security risks of ML without being able to train a model. What matters is seeing how attackers and accidents can abuse the way ML systems learn from data, make predictions, and influence decisions. You will hear terms that feel new, but we will keep them grounded in familiar security ideas like integrity, confidentiality, and availability. By the end, you should be able to describe common abuse patterns in plain language and connect each one to defensive responses that reduce risk in realistic deployments. This is the kind of understanding that helps you spot problems early, before an ML feature becomes a silent weakness. Before we continue, a quick note. This audio course is a companion to our course companion books. The first book is about the exam and provides detailed information on how to pass it best. The second book is a Kindle-only ebook that contains 1,000 flashcards that can be used on your mobile device or Kindle. Check them both out at cyberauthor.me in the Bare Metal Study Guide series. A good place to start is to recognize how ML differs from traditional software in a way that changes the threat surface. Traditional software usually follows explicit rules written by people, so security testing often focuses on code paths, inputs, and permissions. ML systems learn patterns from data, and that means the logic is partly shaped by whatever data you feed them and how you label it. If the data is flawed, poisoned, or biased, the model can behave badly even when the code is correct. This also means attackers can aim their effort at places that are not classic code vulnerabilities, like the training pipeline, the labeling process, or the data sources. Another difference is that ML outputs are often probabilities or scores rather than clear yes or no answers, which can create ambiguity and make it easier for small manipulations to slip past human review. When you adopt an OWASP mindset for ML, you look for repeatable patterns where that difference creates predictable abuse opportunities, and then you build controls around the pipeline and decisions, not just around the application. One common abuse pattern is data poisoning, which is when an attacker intentionally influences the training data so the model learns the wrong lesson. You can think of it as contaminating the ingredients before the meal is cooked, so the final result is unhealthy even if the recipe is fine. Poisoning can be direct, like inserting malicious examples into a dataset, or indirect, like manipulating public data sources that your organization scrapes. The attacker's goal might be broad, such as lowering accuracy, or targeted, such as making the model misclassify a specific kind of input. Defensive responses begin with protecting the data pipeline, including controlling who can submit data, tracking provenance, and validating inputs before they enter training sets. Another defense is monitoring for unusual patterns in data distributions, because poisoned data often shifts the statistical shape of what the model sees. You also reduce poisoning impact by using curated datasets for critical models and by separating untrusted data sources from the core training process. A close cousin of poisoning is label manipulation, where the attacker does not need to change the raw data, but instead influences how examples are labeled. Labels are the answers the model is taught to aim for, like spam or not spam, safe or unsafe, fraud or not fraud. If labels are wrong, the model learns wrong, and it may even learn with high confidence because the labels look authoritative. Label manipulation can happen through compromised labeling tools, bribed or careless labelers, or simply through ambiguous labeling guidelines that attackers exploit. Defensive responses include stronger access control and auditing around labeling systems, plus consistent labeling guidelines that reduce ambiguity. Another defense is having quality checks where a subset of labels are reviewed by independent reviewers, especially for high-impact categories. You can also use statistical sampling to detect suspicious clusters of mislabeled items, which is useful because attackers often focus on a specific target rather than spreading errors evenly. In an OWASP-style view, this is an integrity problem for training data, and integrity controls belong in the pipeline. Another abuse pattern is model evasion, which is when attackers craft inputs that trick a trained model into making the wrong prediction at runtime. Instead of contaminating training data, they focus on how the model behaves today, right now, when it is making decisions. A classic example is a spammer tweaking words, spacing, or formatting to slip past a spam classifier. But evasion can apply to many systems, like fraud detection, content moderation, or malware classification. Evasion works because models often rely on patterns that can be nudged without changing the real meaning of the input. Defensive responses include robust feature engineering and pre-processing that reduces sensitivity to superficial changes, as well as using ensembles or multiple signals so the attacker must fool more than one detector. Monitoring matters here too, because evasion attempts often create a trail of near-miss inputs that look similar. You can also use adversarial testing, which means intentionally trying to break the model during evaluation to learn which manipulations are most effective and to tune defenses before attackers do it in the wild. A particularly important pattern is model inversion and membership inference, which are privacy-related attacks that aim to learn something about the training data from the model's behavior. Model inversion is about reconstructing sensitive features that the model learned, while membership inference is about determining whether a specific data point was part of the training set. Beginners can think of this as asking the model, indirectly, what it remembers about the people and records it was trained on. These risks matter most when the model was trained on sensitive or personal data, or when the model is exposed widely through an API. Defensive responses include data minimization, meaning you do not train on sensitive data unless you truly need it, and access control that limits who can query the model and how often. You also can reduce leakage by limiting the granularity of outputs, such as returning a category rather than a detailed confidence vector when detailed outputs are not necessary. From an OWASP lens, this maps to confidentiality risk, and it reminds you that privacy can be compromised even without a traditional data breach. Another abuse pattern is model extraction, where an attacker tries to replicate the behavior of your model by querying it repeatedly and using the outputs to train their own substitute. This is like copying a proprietary system by watching how it responds to many inputs, even if the attacker never sees the internal parameters. Extraction can be used for intellectual property theft, but it can also be used to make attacks easier, because the attacker can experiment on their copy without triggering your monitoring. Defensive responses include rate limiting, quotas, and anomaly detection for scraping-like behavior, such as repeated systematic queries. You can also consider output restrictions that reduce how much information each response reveals, and watermarking approaches that help identify copied models in some contexts. Another practical defense is requiring stronger authentication for high-value endpoints and separating public-facing models from internal, higher-capability models. This is a place where availability and confidentiality concerns overlap, because extraction attempts can also create expensive load on the service. ML systems are also vulnerable through what you might call dependency and pipeline risks, where the weakness is not in the model itself, but in the tools and processes around it. For example, a training job may pull code and data from multiple places, and if those sources are compromised, the model can be altered or trained incorrectly. The pipeline might include pre-processing scripts, feature stores, model registries, and deployment automation, each with its own access controls and logging. A weakness in any one component can lead to tampering, data leakage, or unauthorized model changes. Defensive responses resemble classic software supply chain protections, strong identity and access management, signed artifacts where feasible, restricted permissions, and clear separation between development and production. You also want change control and versioning so you can tell exactly which model artifact is deployed and what data and code produced it. In an OWASP mindset, this is about recognizing that the ML lifecycle is a system, and the system is only as secure as its weakest link. Another recurring risk pattern is insecure decision integration, which happens when model outputs are treated as final decisions without proper checks. Many ML systems produce a score, like a fraud risk score, and then another system uses that score to approve, deny, or route work. If the integration assumes the model is always right, then evasion and poisoning become far more damaging because the model has direct power. Defensive responses focus on setting appropriate thresholds, adding secondary validation for high-impact decisions, and using human review for borderline or high-risk cases. It also helps to design the workflow so the model's output is advisory when the cost of error is high. Another defense is to keep audit trails that show how the decision was made, including the model version and key features used, so you can investigate when something feels wrong. This is where accountability and explainability become security tools because they limit the model's ability to act as an unchallengeable authority. A related abuse pattern is feedback loop manipulation, where attackers try to influence the system over time by exploiting how it learns from new data or user behavior. If your system retrains regularly using recent examples, an attacker can feed it carefully crafted inputs to shift its behavior. If your system uses user reports or clicks as signals, attackers can coordinate to push the model toward incorrect behavior, either to silence certain content or to allow certain content through. Defensive responses include careful control over what data is eligible for retraining, using trusted sources for labels, and separating untrusted feedback from training without review. You also monitor for sudden shifts in model behavior after retraining and maintain rollback options so you can revert to a prior model if drift is detected. This is an integrity issue that plays out across time rather than in a single request, and it is why secure operations must include ongoing evaluation rather than one-time testing. It is also important to recognize that ML systems can create fairness and harm risks that become security risks when attackers exploit them. If a model consistently makes weaker predictions for certain groups or contexts, attackers may target those gaps because they behave like predictable blind spots. For example, a fraud model that underdetects certain transaction patterns can be exploited by criminals who learn what the model misses. Defensive responses include testing across diverse data slices, monitoring error rates by category, and improving data coverage where the model is weak. This is not about politics, it is about resilience. A model that performs unevenly creates uneven defenses, and uneven defenses invite focused abuse. OWASP guidance often encourages teams to treat predictable blind spots as security concerns because attackers do not need perfection. They only need one reliable gap. Defensive responses for ML risk patterns often come down to a few core themes that you can remember and reuse. One theme is hardening the data pipeline, meaning you protect how data is collected, labeled, stored, and transformed so attackers cannot easily tamper with it. Another theme is controlling exposure, meaning you limit who can query the model, how often, and what the model reveals and outputs. A third theme is robust evaluation, meaning you test the model against adversarial inputs and measure drift over time, not just average accuracy at launch. A fourth theme is strong lifecycle governance, meaning versioning, change control, logging, and rollback are built in so you can respond to problems quickly. These themes mirror classic security engineering, but they are applied to the ML lifecycle. The beginner-friendly takeaway is that you do not defend a model by hoping it is smart enough. You defend it by controlling its inputs, outputs, and change process. One practical way to tie OWASP-style thinking together is to map each abuse pattern to a security objective. Poisoning and label manipulation attack integrity because they corrupt the learning process. Inversion and membership inference attack confidentiality because they aim to reveal training data. Extraction attacks both confidentiality and availability because it can steal value and overload services. Evasion attacks integrity of decisions because it tricks the model into wrong outcomes. Pipeline compromise attacks all three because it can leak data, change models, and disrupt service. When you frame risks this way, you can borrow familiar controls like access control, auditing, segmentation, and monitoring, and apply them to the parts of the ML system where they matter. This is why OWASP guidance is helpful for beginners. It translates new technical ideas into familiar security categories. Once you can speak in that language, you can communicate risk clearly even if you never train a model yourself. As we close, remember that ML security is not a separate universe with entirely new laws. It is security applied to systems that learn from data and make probabilistic decisions. The most common abuse patterns target data integrity, runtime behavior, privacy leakage, and the surrounding pipeline that produces and deploys models. The strongest defensive responses are the ones that reduce attacker influence at every stage. Limit who can inject data, validate and monitor what enters training, restrict what the model reveals, and ensure that decisions are integrated with appropriate checks and accountability. OWASP guidance helps by giving you a structured way to name these risks and match them to controls that are realistic rather than magical. If you carry one simple idea forward, let it be this. Secure ML is less about trusting the model and more about controlling the system around the model. When you control the pipeline, exposure, and lifecycle, you make abuse harder, you make failures smaller, and you keep your organization in charge of how the technology behaves over time.
Thanks for listening. For more audio courses, daily newsletters, and more, please visit baremetalcyber.com.